Look at a raw dataset in wild, and you see chaos. Our goal in statistics is to force that chaos into predictable patterns. But predicting the center of the data, the mean, only tells half the story. To understand the true limits of that dataset, we need to build a precise confidence interval to estimate a population's standard deviation and its variance. We start with what we have in front of us. The sample variance, which we denote as S squared, serves as our single best point estimate for the underlying population variance. Here is where standard logic fails us. If you try to predict a population mean, you build a clean, symmetric margin of error around your estimate. Estimating variance shatters that symmetry. Variance measures physical distance from an average. Because you square those distances, the resulting value hits a hard boundary. It can be 0 or positive, but it can never drop below 0 into negative numbers. This hard floor at 0 requires a specific probability model to govern the math. We call it the chi-square distribution. This chart shows the chi-square distribution in its raw form. Notice the shape. It originates at 0 and pulls heavily to the right. It is explicitly not symmetric. Because the curve itself leans entirely to one side, attempting to apply a traditional point estimate plus or minus a margin of error will output analytically false conclusions. The exact shape of the chi-square curve isn't static. It is governed by a dynamic variable called degrees of freedom, which we calculate simply by taking our total sample size and subtracting 1. As the sample size increases, the architecture of the curve physically responds. Watch how a curve with 10 degrees of freedom carries a sharp rightward skew, but stretches into a smoother, more centralized bell shape by the time we hit 20 degrees of freedom. Yet, even as larger sample sizes push the visual shape closer toward a normal bell curve, the underlying mathematical calculations remain strictly asymmetric. Before we can run those calculations, we must satisfy two non-negotiable requirements. The sample data must be randomly selected, and the underlying population it comes from must have normally distributed values. That normality requirement is exceptionally strict. When estimating means, the math can forgive minor deviations. Variance estimation offers no such grace. Proceeding with a chi-square estimation on a population that departs even slightly from a normal distribution will generate massive cascading errors in your final limits. Do not assume normality. Before executing a variance estimation, the integrity of the population's distribution must be indisputably proven. Let's test this in a clinical setting. We are tasked with estimating the standard deviation of adult female pulse rates, drawing from a raw sample of exactly 22 patients. This normal quantile plot shows our raw clinical sample. Because the data points align tightly along a straight line pattern, we have verified that the sample originates from a normally distributed population. We are clear to proceed. With a sample size of 22, our degrees of freedom drops down to 21. We need to establish a 95% confidence interval. That leaves an alpha level, or error allowance, of 0.05, which we split equally into two distinct tails of 0.025. To translate those tail areas into usable limits, we must consult Statistical Table A-4. Here we encounter a common algebraic trap. Standard Z-tables read cumulative area from left to right. Table A4 forces you to read cumulative areas exclusively from the right. To locate the right critical value, we map our 21 degrees of freedom directly to the 0.025 area at the top of the table. This locks in our critical value at 35.479. Finding the left limit requires a counterintuitive mental shift. Because the table forces a rightward read, we must look up the remaining area, 1 minus 0.025. We map our degrees of freedom to the column for 0.975. This graph displays the complete architecture. We now have two highly asymmetric critical values anchoring our curve, 10.283 on the left and 35.479 on the right. Navigating variance requires analysts to actively override their standard reading instincts when they are interrogating these complex statistical tables. We construct our confidence interval using a three-part inequality formula, isolating the population variance right in the center. Now we apply the denominator inversion principle. Watch closely. The larger right tail critical value slides into the denominator of the lower left limit. The math here is strictly inverse. Dividing the sample variance by a larger chi-square number mathematically forces the lower bound down. Conversely, the smaller left tail critical value goes to the right side fraction, driving the upper limit higher. We execute the calculation by plugging in our clinical pulse rate data, our sample size of 22, our sample variance, and those two specific critical values. The algebra resolves to establish our population variance estimate. The bounds sit firmly between 58.2 and 200.9. To translate this back into a standard deviation, we perform one final mathematical step, taking the square root of all three components of the inequality. This tightens our window. The standard deviation for adult female pulse rates falls somewhere between 7.6 and 14.2 beats per minute. Notice the exactness of the figures. We apply a strict statistical round-off rule, taking the confidence interval limits out to one more decimal place than our original raw data. We are now 95% confident that the true pulse rate standard deviation actually lies securely within these specific bounds. Our starting point estimate sits inside this window, but the interval extends much further to the right than the left, proving the math is completely asymmetric. Analyzing existing data is only half the job. In experimental design, you must determine how large a sample must be to guarantee accuracy before collecting a single data point. The algebraic procedures for isolating required sample sizes for standard deviation are vastly more complex than calculating sample sizes for simple proportions. The equations are so dense that standard software platforms, as well as basic graphical calculators, completely lack the built-in functions to run them. Analysts rely entirely on specialized statistical software like StatDisk, or they map their requirements against pre-calculated industry reference tables. Let's set a strict design parameter. We demand to be 99% confident that our estimate will land within a tight 5% margin of error. When we consult the reference table, intersecting a 99% confidence level with a strict 5% error allowance reveals our target number. The required scale is massive. To achieve that exact level of precision for variance, the clinical experiment requires a sample size of 1,336 patients. Rigorous variance estimation leaves no room for assumptions. It demands that you abandon the comfort of symmetry, ruthlessly verify data normality at every step, and rely on specialized tools to navigate the heavy math underneath the curve.